person finally. Time we talk about reconfiguration.
Yeah.
Please.
Thank you, Samuel, for the invitation and for the opportunity to entertain everyone with reconfiguration of graphs, where we will speak about precise diameters of reconfiguration graphs that depend on some colorings of graphs. To start with, I want to mention that this is based on joint work with Wouter Kames van Batenberg from the Netherlands and Daniel Cranston from the USA. And the project itself started from a workshop called Graph Reconfiguration, which was organized online, virtually, by the Sparse Graph Coalition. So it's a workshop which is held online with like 30 people who work together in groups, so it's a nice initiative. And after a year, there was a paper which came out of this, which I will partially mention since it contains some more results. But okay. Before being able to mention some results, obviously I need to be sure that everyone can understand, so all concepts should be clear, so diameter and configuration graphs and so on should be clear. And then afterwards we want to introduce the two main conjectures. One is about list coloring and another one about DP or correspondence coloring. But let's start with the concepts. And to be sure I do not have to explain all of them, here's a list of a few concepts. So if any of these is not clear, please ask, and then we at least can be sure that everyone is on the same page.
So what is the diameter in graphs?
Yeah, so I can.
Distancing.
Okay, so you know about the diameter, about distances in graphs?
Shortest distance between two vertices?
Yeah, so the shortest distance between two vertices, for example here, L and M, is equal to the length of a shortest path, so presented here in dark blue from L and M, so in this case the distance is 5. You can do this between any two vertices. In this case, all of the distances will be at most 5, so the diameter is the largest distance, and that will exactly be equal to the diameter. So a formal definition is here, so the distance, and then the diameter is equal to the maximum. No problem. Okay. But so proper colorings, list colorings, everyone knows about this. Cliques, independent sets, some basic graphs, so the degree of a vertex and the maximum degree, the matching number, and the vertex covering number.
Could you explain a little bit about list coloring?
About list coloring?
Yes.
Yes. Right. Okay. Cool. Yeah, so a coloring itself is called proper if two neighbors have a different color, and instead of just having some colors you can choose yourself for every vertex, some opponent or there is some restriction, you have to choose a color from a list. So formally, so you will have a list assignment, so a mapping L which associates some number of colors. So basically we will represent every color with an integer. If all the lists have the same length k, then this is just a k set of integers for every vertex. You choose a color from this list for every vertex such that you attain a proper coloring, and then you have a proper L coloring. Okay. And the remaining of the concepts were clear. So here was quickly about vertex covering. Okay, so once all of this is clear, I first want to mention about reconfiguration in general. So reconfiguration can be about almost anything. So you have some objects and you want to reconfigure them, so slightly adapt them, where you have some possible allowed changes. So you can have some small step and you can repeat this to go from one instance to another instance. So for example, in the abstract, there was written about a Rubik cube. So you can do one turn and then your Rubik's cube will have be in a slightly different configuration. Some colors will have changed and you can repeat this. And in that case, you want to end up with a base configuration where all 6 faces have one color. As another example, we also have, for example, the 15 puzzle. So you have the numbers 1 up to 15 on these cells or pieces inside a 4x4 playing field. And you can move one piece at a time. So one movement. So, for example, putting
Actually, if you hold it and then try.
okay, it worked a few minutes ago. Okay. Okay, so for example, moving 15 to here will be one move. So that could be considered as the reconfiguration of this. And so in the 15 puzzle, you start with a kind of random configuration and you want to order the numbers. Okay. And then another example will be here where you need to swap 15 and 14, but actually practically this is impossible. So there is some invariance you can find to prove that it's not possible to reconfigure this one into this one. So in general you have something you want to reconfigure, you have some base object, so an instance can be just any arbitrary choice of your numbers 1 up to 15 on this 4x4 grid, and then you can think about having one step, and then one question is to know if it's possible to solve the puzzle in the sense that you can reach the base configuration. Okay. Okay, so that's the idea about reconfiguration, and it also can be applied in some cases. So, for example, if you have your firewall at your computer which protects everything regarding Trojan horses and so on, then you quite often have these updates. So then your firewall will be updated, but they can't just delete your firewall and replace by another one, since if the download will take an hour, during 1 hour, like all the spyware and whatever could come on your computer for free. So you have to do small steps. So you have to update it in such a way that at every point your spyware or your firewall is still good. And there are also other questions. So for example, if it's about assigning frequencies to networks, so this is a problem that's often associated with list coloring, but this problem on its own is NP hard. So when Google or other big companies have a heuristical solution which is nearly optimal, they have implemented it, and maybe after some more runs they found a better solution. They need to reconfigure, so they need to change frequencies in such a way that they do not cause troubles meanwhile. Yeah, and there are some other cases like local search is about finding some optimum, where you look in a region if you can find some better solution and then you repeat. Okay. And now instead of just having this concept of reconfiguration in general, we will associate a graph on this. So every possible allowed or even not allowed instance, so for example every possible configuration of your 15th puzzle is an instance, so we will represent this as a vertex of your reconfiguration graph, and two vertices are connected precisely with one move. You can go from one instance to the other.
Should we think of it as a directed graph?
Oh, in these cases the movements are like symmetric.
Okay.
Yes, so in the case of the 15 puzzle, you can move your 15, but you can also put it back, and also in the other examples we will see this is the case. But yeah, obviously you also can have directed reconfiguration, but we will speak about a somewhat more symmetric case of the graph case. Okay. Once we have such a graph, so for example you want to solve the 15th puzzle or the Rubik's Cube, finding the most efficient way to reconfigure is precisely finding the shortest path between two vertices in this reconfiguration graph. So there are a few questions which could be interesting to solve. So for example, if you have specific instances alpha and beta, you want to find the shortest path from alpha to beta, or you just want to know if you can go from alpha to beta, or as was the case in the second example of the 15 puzzle. If that's not the case, you need to prove that the graph is disconnected or there is no path from alpha to beta. If you know there is reachability for some instances, and this is the case for all of them, then you have proved connectedness of the reconfiguration graph. So there are quite a lot of cases where it's interesting to know if some general reconfiguration graph is connected, and if you know about that the graph is connected, you also can wonder about how fast you can reconfigure in general. So the diameter of the reconfiguration graph tells something about the worst case, so knowing the diameter is an interesting question. And today we will apply these questions on some specific reconfiguration graphs where we speak about some colorings of graphs. So our vertices or our objects will be proper colorings of our graphs, and the reconfiguration, so our small steps, will consist of recolor one vertex in such a way that you end up with another proper coloring. So the allowable change will be recolor one vertex in such a way that we end up with another instance, so with another proper coloring. And more specifically, we have a few cases. So on the one hand, we can have the reconfiguration graph with k coloring. So you fix some number k, and you can look to all possible proper k colorings of the graph and build a reconfiguration graph. And note that if k is smaller than the chromatic number, then the reconfiguration graph is the empty graph. You can also speak about list coloring. So in that case, you fix your L, so your list assignment and your graph, and you have a reconfiguration graph using all proper list colorings, and also again with some connections in between if you only have to recolor one vertex. And the same does exist for DP coloring or correspondence coloring, which I will mention at the end, as correspondence coloring is not that known probably to everyone. Okay. So now I have told what it is, but obviously you can represent it. So for example, here you see the reconfiguration graph C3 of K2. So K2 is a small graph, only two vertices, three colors. You have three colors for the first vertex, two for the other one, 6 proper colorings in total. You can note that here we only recolor red and yellow or reverse. And we see this is a C6, so this is an easy case, and there are some other cases which are easy. We can mark if we have the two colorings of an even cycle. So if you have to recolor an even cycle with red and blue, you color a first vertex and then everything is determined, since the neighbor of a red vertex has to be blue and so on. So there are only two proper colorings, but you can't reconfigure one into another. So in that case, the reconfiguration graph only contains two isolated vertices. And similarly, if you have a cleat on k vertices, you have k colors. You have k choices for your first vertex, k minus 1 for the next one, and so on. So you have k factorial proper colorings, but you can't recolor one vertex, as it already has k minus 1 colored neighbors. So only one allowed color for itself, and it's already colored like this. So again, this will be a stable set, an independent set with k factorial vertices. Okay. As a next example, so we have seen that C3 of K2 was the C6. Now, if we speak about list coloring, already for K2, the reconfiguration graph can be different. So assume that there are two lists on both vertices of length 3. And these colors are different, then you basically can reconfigure any vertex since you won't have any obstruction. And in this case, you have 3 choices for both sides. So basically, the reconfiguration graph is the Cartesian product. I hope it looks like this. It's so the reconfiguration graph is the Cartesian product of two K3s. And now I have a question for you. It should be a bit of interactive. So now we have still the K2, so a fairly simple graph. It's not K1 because then it's not a question anymore. The lists both have 3 colors, but one of them is equal. Okay. how does the reconfiguration graph CL of K2 looks like in this case?
Is it the Cartesian product of P2 and K3? Maybe? No.
So maybe a first question, how many vertices does this reconfiguration graph?
Okay, yeah.
Just remove one vertex from the previous graph.
Yes, so indeed it's closely related to the previous graph. It's actually, we have the same graph, but one color is the same. So if you have red, blue, yellow, and red, black, white, then red is not allowed. But different from that, it's the same. You just can consider red prime. You can do whatever you could do before, and only red is forbidden. So it's indeed like you remove one vertex. You could do the same if two vertices, if the two lists have two colors in common, then you can remove a second vertex, which you have to, you can choose it here. And our previous, like our base case, the C6, is actually also like a subgraph of the Cartesian product of K3 and K3. If the three colors are equal, then we have to forbid, for example, red, blue, blue, and yellow, yellow. And we see that this induced subgraph is precisely the C6. Also mentioned here, so the diameter in this case equals 2. It will already be equal to 3 when the lists have two colors in common, and C6 also has diameter 3. So if we are speaking about list coloring, and we know the size of the list, then we don't know the precise diameter actually. Okay. Just some observation. Much more will be mentioned in the second part of it. To end this introduction about reconfiguration, I want to mention one old problem on the reconfiguration graphs already. And there was a conjecture of Horak which was actually false in many cases, but there is one remaining case in which it seems to be true. And okay, that's if you have your so now we are again speaking just about the reconfiguration graphs of coloring. So we have all three colorings of a graph, and actually you may assume G is bipartite. And we know that C3 of G is connected, so we can reconfigure from any tree coloring to any other tree coloring. Then it's conjectured that this graph will be two connected. So for example, the C6 is clearly two connected, and this conjecture says that this is the case in general. Basically for k larger than 3 this was false, so there was an analogous statement, since in that case you could have vertices with degree 1, so you clearly, its neighbor is a cut vertex, so it wouldn't be two connected. But I already could observe that this is not the case when k equals 3. Okay, so people who want to think about this later, please contact me. Okay. Now I can give a little break, maybe you solve it during this this time, but just to be fresh. So, oh, it's already too fast. Since it's a talk about 50 minutes or an hour, that's important. You are relaxed and it's not too long. So that all concepts now are clear, and so soon we can really speak about these diameters of list reconfiguration graphs. So I hope all of you are ready by now, not with solving the previous problem. Otherwise I will feel bad, I talked already a few weeks about this. Okay. But so I want to go on with the diameter of reconfiguration graphs, and actually the inspiration is by Cereseda's conjecture. And Cereseda's conjecture is about the diameter of reconfiguration graphs, where you just have k colorings, and k has to be at least a degeneracy plus 2, and it conjectures that the diameter is big O of n squared. So this is not a precise bound, but it says, okay, it's quadratic, and it will be sharp if true. But I will tell more on this at Xiam, and there it's a talk of just 15 minutes mainly on this. But today the story is slightly different, so this was the inspiration. I won't mention that much about it today. But based on this, we look to two nicer conjectures somewhat, because they are about precise diameters. And as was the case with Cereseda's conjecture, but also because we need to have a connected graph to speak about the diameter, otherwise it can be infinity, and it's not that interesting. We need to have some condition that ensures that the reconfiguration graph is at least connected. In this case, we want to have a minimum degree condition, and we can observe. So, for example, I mentioned the CK of the clique on K vertices was just a bunch of isolated vertices, and we can do something similar in general with list colorings. If all lists of every vertex has size precisely the degree plus 1. So, for example, here we have a graph, and we basically take a proper 2 coloring. So no two vertices of distance 2 have the same color. For every vertex, we take its list being equal to the color the vertex has, plus the colors at its neighbors, which are disjoint. So in that case, all lists have degree V plus 1 colors, and we can't reconfigure, since we can't recolor red with green, since its neighbor is green, same for black and blue, and the only remaining color is red, it's already red. And it's also not a hard task that with this list assignment you can find multiple colorings. So in this case there might be some, the reconfiguration graph is not necessarily a bunch of isolated vertices, but it has at least one. It has multiple vertices, so it's disconnected. And in that case, we can speak about the diameter. So we want to have larger lists, and so we knew that degree V plus 1 is not sufficient. It feels also as a natural condition that the larger the degree of your vertex, so the more neighbors and the more obstructions you can have, the more colors you want to put in the list. So a natural choice was to take the size of the list to be at least degree V plus 2 for every vertex V. And this is also related to Cereseda's conjecture, where you had degeneracy plus 2, but there is a difference between list coloring and proper coloring. Okay, so I hope this is already a natural setting to start with. So we want to know about the diameter of a reconfiguration graph, so a list reconfiguration graph, where all lists are somewhat large, so that it's easy to prove that this is connected. And, we want to make some other observations. So a first observation is, if you have a vertex which is in your first instance colored blue, and in your second instance it's colored red, at some point we will have to recolor this vertex. At least once. So we can recolor from blue to green to red, but at least we have to recolor once. And if we have an edge, like this one, and so under alpha it's at the left it's colored blue, at the right it's colored red, and here the two colors are swapped, then we will need at least 3 recolorings to recolor that edge, since we can't recolor the left one in red since it's neighbors. We can't recolor that neighbor in blue as long as the left one isn't recolored, so we need at least 3 colors. So basically this gives some upper bound, which is sharp in some cases, in the sense that if we have a bipartite graph or a complete bipartite graph, and we want to switch the colors of the two color classes, we can't recolor any vertex on the left with blue as long as there is a blue neighbor, and similarly at the other side. So I hope in this case of the K43, it's natural that first you want to recolor the 3 blue ones, for example in green. So we have 3 bad recolorings which are not efficient. After that we can recolor all red in blue, and then all green meanwhile in red. So we need 10 recolorings. So the distance between these two colorings in the reconfiguration graph C3K for 3 is at least 10. That will also be equal to the diameter, so one can verify that. So that's one case where basically you have 3 independent edges. So we needed 3 recolorings for such an edge. There's the color swap. We have one remaining one which has to be recolored. So we have 3 times 3 plus 1 is 10. So 10 was a lower bound, and in this case it will be sharp. And in general, for list colorings, you even can prove that for every graph G, you can construct a list of size precisely degree V plus 2 for every vertex V, such that the diameter of your list reconfiguration graph is at least the number of vertices, which is the trivial number of recolorings. If you just pick 2 colorings such that every vertex has a different color under alpha and under beta, plus some additional ones, mu, so the matching number, since the matching number denotes the maximum number of independent edges, and you want to have edges such that the colors switch, as mentioned before. So basically, I first will prove it by means of pictures, and then afterwards there is some formal proof. If we have some random graph, we pick a maximum matching. We want to ensure that for the vertices which do not belong to the matching, just we have a color under alpha and a color under beta which is different. And for the endpoints of an edge in the matching, so for example the 2 blue ones, we want to assign 2 colors so that we have 1, 2, and under the other one 2, 1. We do this for every edge. And then the formal proof you can do so is given here. So we took a maximum matching. If 2 vertices are the end vertices of an edge which belongs to the maximum matching, we take their lists such that there are precisely 2 colors in common, and they are disjoint from all other lists. Okay, and we take a disjoint list for vertices which do not belong to a maximum matching, or to a fixed maximum matching. Then we don't have any obstruction about choosing those 2 colors which are in common as the colors of the end vertices of this one selected edge, because all the other lists are disjoint. So we can have the swap, and so n plus mu was really a lower bound. Okay. So in that sense, n plus mu seems like a nice bound. So the nice list recoloring reconfiguration conjecture, or list conjecture for short, says that this is actually also an upper bound. So for any graph G and every list assignment such that the sizes are at least as degree plus 2, then the diameter of our list reconfiguration graph will be at most n plus mu. And note, in certain cases, for example, if all lists are disjoint, then n is an upper bound as well. But so n plus mu is an upper bound in general, which is sharp in the sense that, due to the previous proposition. We could prove this in a few cases. So it's already verified, for example, for cactus graphs, so for example for cycles, for complete graphs, and for complete bipartite graphs. So as I gave the example of the K3 form, maybe you can already visualize in the sense that you only can recolor towards a color that's at the other side once you removed the other side. We also could make some partial progress in the sense that we proved it in 2 ways up to a factor 2. So we could prove that the diameter is at most n plus 2 times mu, so at least also this matching number is natural in the sense that we know that n plus 2 times mu is an upper bound and n plus mu can be a lower bound. And we could also prove if our lists are even larger, so instead of degree v plus 2 we take 2 times the degree plus 1, then this bound is completely proved. And to end this second part, I want to give a few mathematical proofs, so the pictures are left for a moment. Okay. And as a first step, like a year ago, we first proved that 2n is actually an upper bound for the diameter, and that was the first linear upper bound that was known for these diameters. But this could even be easily improved to 2n minus 1. So if all lists are as large as mentioned before, so this degree plus 2, and we pick two list colorings, L colorings, alpha and beta, then we can reconfigure them in at most 2n minus 1 steps. Yeah, it's a lemma, so I also have a proof, which is basically induction. You consider the number of color classes under beta. Okay, if this would be 1, so you want to recolor all vertices in one color, and it has to be proper. This actually implies that the graph itself is just an independent set, a stable set. Recoloring a stable set can be done in n steps. N is at most 2n minus 1, so that's fine. Okay. If that's not the case, and there are some vertices which are already colored with its final color, so alpha v and beta v are equal, you just can discard v, since it's already colored fine. So you do not have to care about this one, you can remove it. You can remove the color when necessary at the list of its neighbors. The degree of these neighbors have decreased by 1, and also the list sizes have decreased by at most 1. So we can apply induction, so that's fine. So we can assume that all colors, all vertices are colored differently under alpha and under beta. That's somewhat the worst case. Now, under that case, so for if you consider the number of vertices colored by 1 for alpha and beta, you do this for color 2, etc., for all colors, there is some color that appears at least as many times under beta as under alpha. So for example, if color 1 appears 5 times as the color under alpha and 7 times under the coloring beta, then what we will do is we recolor those 5 vertices under alpha. Every vertex has degree v neighbors. Okay? And the list has degree v plus 2. So at most degree v colors are forbidden, and we forbid our color 1. So there is one remaining color, so we can recolor these 5 vertices so that color 1 is not present. But so beta minus 1 of 1. So all vertices that are colored under beta with 1 are an independent set, so you just can recolor all of these independently with the color 1, as 1 was not present. So now we have used 5 recolorings to remove 1, 7 recolorings to introduce 1, and now 7 vertices have their final color. We only used 12 recolorings, which is less than 2 times 7. It could be equal, 14. Now we can just apply our induction. We remove these 7 vertices as before, and we repeat, and then we have almost 2n minus 1. And here you see some formulas which give this into it, or say this with general numbers instead of 5 and 7. Okay. And with this, we can prove our n plus 2 times mu bound, since basically we already proved it for factor critical graphs. So those are graphs so that if you remove a vertex, the matching number will be the same. And these have the condition that the number of vertices is, there are like multiple equivalent definitions for factor critical graphs, but such a graph has an odd number of vertices. And once you remove one of them, you can find a perfect matching. So n is precisely equal to 2 times mu plus 1. So in that case, n plus 2 times mu equals 2n minus 1. So that case has been tackled in the previous lemma. If that's not the case, there does exist some vertex v, such that g without v has a lower matching number. So basically, removing v will decrease mu strictly, and it decreases n, both with 1, and n plus 2 mu will have decreased with 3. So we have 3 additional recolorings to play with. And that's exactly what we will do. So we pick some vertex v such that the matching number decreases by 1. We have both under alpha and under beta, we have degree v neighbors which might have a different color. that we have degree v plus 2 different colors at v. So some color appears at most once under alpha and beta. And by switching alpha and beta if necessary, you can assume that this is the case under alpha. Okay. So then, in the worst case is when there is precisely one neighbor which has this color C. So, for example, initially there is one neighbor which has color 1 under alpha, and there is no neighbor which has color 1 under beta. Then first, as done before, we can recolor this 1 into some other color, as the degree v plus 2 gives, like, you have some additional color. We recolor this one. Next, we can recolor v with the color 1. We can remove the color 1 in its neighbors, so we do not have to care about v anymore, since no vertex over there wants to have color 1. Now we can apply the induction, so we have like this n prime plus 2 times mu prime, where n prime is n minus 1 and mu prime is mu minus 1. So by induction we have, so basically here, so we have 2 recolorings at the beginning, or induction implies that we need at most n minus 1 plus 2 times mu minus 1 recolorings. Now all vertices have color beta of v, except maybe the one we picked, which we have colored by 1. If necessary, we recolor this one, so 1 additional recoloring, and so by induction we found n plus 2 here. So that's, there was a question? Okay. I'm happy this is clear. So this is the idea for one of the 2 proofs. So I didn't do the other case. Like there are basically 2, in the theorem there are 2 cases where we have factor 2 off, and the other one I will give as an example for the DP conjecture. So I hope this gives some intuition about the conjecture, and like I hope all of you find it a nice conjecture. So the main message is that these things have been studied before, and so Cereseda's conjecture gave like some quadratic upper bound. But then you have a pretty vague upper bound in the sense that there are even 2 forms of this conjecture, where they tell like, okay, like it has to be at most a constant times n squared, but actually this constant might even depend on the degree, which is partially cheating. Since if you have kn, then the maximum degree, which is n minus 1, is basically n. So in that sense, even the conjecture is not precise. So this was one conjecture. And while thinking about the list conjecture, we were also thinking about a generalization of list coloring. Does everyone know about TP coloring or correspondence coloring? No? Luckily, otherwise I would have prepared 10 other slides, which are not necessary. Okay. So basically, like with list colorings, you are really speaking about colors. Wait, this is still part of the break somewhat. If you don't like colors, we're just gonna build bigger graphs and speak about independent transversals. So then we get rid of all these annoying colors. And so in that sense, we want to generalize list coloring. So for example, if you have a C5 and we have lists of length 3, then you can look to the list which have 3 colors. So for example, this vertex has a list with blue, yellow, and green. So these are the list of its 2 neighbors. And if some colors are the same in the list of neighbors, so for example, this one is blue, this one is blue, then it's not allowed to pick blue at a proper coloring for both vertices. So now what we do, we have this cover graph. So instead of having our C5, we have a subgraph of a blow-up of the C5 with 15 vertices. And we connect, so every pair of a vertex and a color in its list is represented by a vertex. And we connect 2 vertices in this cover graph if the correspondent vertices, so the 2 blobs, were initially neighbors and the colors are the same. So in that sense, in this case, we get this pretty nice cover graph. Okay. Well, we still see colors maybe some of you didn't like colors, so we do not have to care about the colors anymore. So everything about finding a proper list coloring is now inside this graph. We want to find a vertex in every list, which corresponds to a color in every list, such that we have selected an independent transversal, as then automatically, like the vertex neighbors have been colored with a different color. So in this case, we can find a transversal like this. The initial list cover is like this, and so we can see 5 colors. So we have found a proper list coloring of the graph. If you return to our to this graph, what we see is we have some blobs with 3 colors, and then between we have some matchings which correspond to equal colors. But in the generalization, we don't care about colors anymore, so we just put random matchings between them, and then we have a generalization. Maybe let's do it first like this. So for example, we have a C5, we take blobs of size 3, and we put matchings. And the hardest case is to have perfect matchings in between. But now here, we put the identity, which can be done without loss of generality, except from the last one. So now we see this cross. And it's not hard to check. If this vertex is red, this one is red, we can repeat. And then this one should be red, so we would have twice red. And then, this does not correspond to our initial list coloring problem, so this is very different. And this is a generalization which is called correspondence coloring. So what we will do is, instead of having lists of colors, we will have a correspondence assignment. So we have some L of V, which just contains some fixed K vertices, colors, or elements, how you want to call them, such that there is some matching between these lists. So whenever VV prime is an edge, you have a matching. It doesn't have to be a perfect matching, but that's the hardest case between the two lists. Okay. And once we do this for every list, every pair of lists corresponding to 2 vertices which are neighbors, we get a correspondence cover which looked like the previous picture. And the correspondence coloring will be precisely 1 vertex of every blob, so that it forms an independent transversal. So it's an independent set in the cover graph with 1 element in every LV. Okay. So this was an example. Now we can find a correspondence coloring. So we have selected 5 vertices, 1 in each blob. So somewhat if you want to speak about just, for example, in the computer where you want to find, or verify that the correspondence chromatic number of this graph is 3. So then you look to all possible matchings. There are actually only 6 of them. Putting here a K3, so there should be an edge like this. You just can check, okay, in all 5 cases, is the independence number of this graph equal to 5? If that's the case, in all 6 cases, you conclude. Okay. So in that sense, it's much easier to verify but with a computer that the correspondence chromatic number of some graph equals some K, since you only need to check some finite number of matchings. Somewhat in the sense with colorings, you have infinitely many colorings, so you don't know about your list, so it's harder and easier depending to which problem you are looking to. And that makes it interesting. So this correspondence coloring has been defined some years ago by Dvorak and Postel, and that's also why some others call it DP coloring. Okay. So once we know about correspondence coloring, we are speaking about reconfiguration graphs. So for a fixed correspondence assignment of a graph, we can look to all possible correspondence colorings. We can put edges if you only have to move one vertex. So, for example, here, this is one correspondence coloring. But we could replace this one to here. So we could reconfigure, so which is kind of recoloring this vertex in the correspondence coloring setting.
So in the previous lower bound, oh, this is for some choice of emanating. I see.
Yeah. So we can build some reconfiguration graphs again with this correspondence coloring, and then it's about, okay, our first question was, is n like n plus mu, would it also be an upper bound for the correspondence coloring? And we had some partial confirmations, and it was like, okay, yeah, we have like our general proof, which is pretty good. Okay, and it works all except from that, from one lemma. So we just need to verify one claim, and then we know like n plus mu is also sharp. But then it turned out it's false, and so kn is already a counterexample.
So here, don't you have to assume the size of L for each vertex? So the size of list is something, the degree plus 2? Or?
Yeah, indeed. So we also take the list equal to at least degree plus 2, even while for the counterexample it's not that important. Okay, since yeah, indeed. In this case, I needed to have like list of length 7 instead of length 6 instead of 5, for example. So we had these blobs of vertices, and in between we have some matchings. Okay, and you can extend this to perfect matchings, but then there are way too many lines. The important thing is we have selected one favorite vertex in every blob, which has been colored red, a second favorite one in purple. These are the correspondence colorings alpha and beta. So one can note that every red vertex now has been connected with the purple ones and vice versa. So if we want to reconfigure this graph, or reconfigure the correspondence colorings from the red one alpha to the purple one beta, we only can recolor red into purple if the 4 neighbors are not colored red. But that's true for all 5 of them. So we need to do 4 bad recolorings before having one efficient recoloring. And in this case, so all except one is n-1, so we will have at least n-1 bad recolorings before doing n efficient recolorings. And this gives a lower bound of 2 n-1, while the matching number mu is at most n over 2. So that's not the case anymore. So the correspondence conjecture will be different. And in general, we can prove that, so for every graph, there exists a correspondence cover such that the number of elements in L of V is at least degree V plus 2 for every vertex, so the same constraint, and such that the diameter is at least n plus tau, where tau is the vertex covering number. And the construction is pretty similar to the clique. So we can call the colors or the elements in L of V, V1 up to V, degree V plus 2. And then we connect V1 with W2 and V2 with W1. So basically you will have the same crosses. So if you want to recolor V1 into V2, then for every number W, it's forbidden to be colored with W1. So basically to recolor one vertex efficiently, all its neighbors have to be recolored inefficiently. So basically if you have an edge, again, for every edge you will have to recolor 3 times. So you will have some loss. So basically if you want to have some vertex set such that no edges are spanned by them, you need to find an independent set. So you can find at most the independence number many, and the covering number, the vertex covering number, is actually equal to the complement, so it's n minus tau. Tau is n minus alpha, where alpha is the independence number.
So but that It's a lower bound, right?
Yeah, indeed. But so this lower bound is also for some L. So this is somewhat a hard case where we need at least n plus tau many recolorings. But now our nice
But proposition, you said equality here. Is it typo or?
so there exists yeah indeed for this case it's easy to verify its equality. But so yeah that's yeah in general it could also be stated with at least. But this is just one example. So for this specific case it's precisely equal to n plus tau. But yeah, at this point actually it's not known that it can be larger, but we conjecture that's not the case. So we conjecture that n plus tau instead of n plus mu is an upper bound in this correspondence version. So this is the second main conjecture I want to present. So if we have any correspondence cover, so which is a bit as the previous ones, with the same constraint, then the diameter of the reconfiguration graph is at most n plus tau. And that's again like a sharp result due to the previous one. And exactly due to that, it's nice because then it's like a precise upper bound. And people in graph reconfiguration have considered many questions about finding upper bounds. But yeah, they do barely have any sharp versions, and this is something about any graph. And somewhat we could prove the conjecture in similar cases, so we could do it for qubit graphs. So if the maximum degree is small or the maximum average degree is small, we could verify. And again, it's true for cactus graphs, so cycles are a case. But actually, it's not proven yet for complete graphs, which is a bit weird, since I proved that for these specific correspondence covers, it's equal to 2n minus 1. But yeah, there are many ways to choose your perfect matching, so it might be in some sense that it's even larger. And the cliques are already a pretty hard case, surprisingly. Okay. And as I mentioned, we can prove two analogous statements which are sharp up to a factor 2, so we can prove that n plus 2 times tau is an upper bound, similar to the proof before, well, somewhat similar. And we can prove it if the lists are larger, so 2 times the degree plus 1. Okay, so with the right form, and I want to end with the idea of the proof of that case, since in this case the proof is actually easier than in the list recoloring conjecture, which is maybe surprising. In this case, so we have to prove that n plus tau is an upper bound. Tau is the size of a minimum vertex cover. So something natural to do is pick a minimum vertex cover, so which is the complement of a maximum independent set. First, we will recolor every vertex in this cover. We have 2 times degree plus 1 colors. We have degree v neighbors, so we can consider, okay, degree v colors are forbidden. No, but there are also degree v colors under beta. We forbid these as well, and we pick a different color. We do this for all of them, since we have one available color. Once all of these are recolored, we can look to the remaining vertices, which form an independent set. We just can recolor them with their final color. Once we have done those, we can look to S again. So for every vertex in the cover, we also just can color it with its final color. And so then we have tau plus alpha plus tau, tau plus n minus tau plus tau, n plus tau colors in total. So, well, we have recolored every vertex at least once, and every vertex in the vertex cover twice. And that's the idea. And that was basically the talk in which I presented those two conjectures, which hopefully feel as appealing to you as to me and my co-authors. So in the list coloring version, we have n plus mu, so the number of vertices plus the matching number, and the corresponding vertex n plus the covering number, and both of these would be sharp if true. That would be pretty nice. And this would imply a regular version of Cereseda's conjecture, which is linear instead of quadratic, and not just linear, but sharp. And more on this on Friday. Oh yeah. just shorter titles. So list conjecture, DP conjecture as well. Like, minimize the storage in your head. For Thanks. I thank you for your attention.
Thank you. Any questions?
So you mentioned, I think a few slides back, something about graphs of low maximum average degree or something.
Yeah. So it's up to maximum average degree 2.4. And
Oh, okay.
And the proof for that is with discharging.
Uh-huh.
So it's like, if you have maximum average degree at most 2.4, you can forbid some structures. So particularly the maximum average degree is at most 2.4. You have a vertex of degree 1 or 2. And these are somewhat easier since you only have to care about 1 or 2 neighbors.
Mm.
And then you also can tell something about the degree of the neighbor. So that's a discharging argument. Yes.
So may I I want to add some algorithmic aspect. So I'm not sure, but what I remember is that for general graph, deciding whether there is a reconfiguration or not is p-space complete problem.
Yeah,
And
it's hard in certain.
yes, and in the proof of list, so proof of some weakening of list conjecture, then it looks like that not only just show that diameter is small, but also it gives some polynomial time algorithm to find
Yes.
such paths. But in the proof weakening of DP conjecture, then in the proof looks not working in polynomial time because we need to find the minimal vertex cover. Then what I want to ask is there some complex result for such case, or it is just there might, we don't know there exists some polynomial time algorithm or not.
I don't look that much into algorithms, that's one. And two, as I mentioned, even the complete graph is still open. So if you would have a polynomial algorithm, we would be able to verify for small cliques, which we actually didn't do yet. So we didn't think about algorithms. One thing is we know that in general, indeed, like these are hard problems, but precisely due to these constraints, so we tell the lists are pretty large. Due to that, it's easy to verify that it's connected, while in general, even knowing the connectedness might be hard, as you mentioned. So part of the answer is we have this condition, and for the precise diameter in general, I don't know about polynomial algorithm, since also when n plus mu is an upper bound, and even like in our proof we give a simple algorithm to do so, that doesn't imply that n plus mu is hard for every list coloring. So I don't know about an efficient algorithm to prove the sharp version. Since, for example, if you know about the radius of a graph, so it's similar. So the diameter is about the maximum distance, and the radius is about finding a vertex which is somewhat central, so that the maximum distance between this vertex and any other one is at most r. And the smallest r for which you can find such a vertex is the radius. So we could construct some trees for which that and list coloring, a list assignment such that the radius is nearly n plus mu over 2, while the diameter is n plus mu. So there are really differences. I hope this gives some stuff related to your problem and which is interesting to you.
I just wonder, just DP conjecture. So I just wonder under that assumption L is n is degree v plus 2, then I just wonder, can we find some path of length n plus 2 times tau in a polynomial time or not? But
oh yeah, for the n plus 2 tau.
So you prove that in that assumption diameter is bounded by n plus 2 times tau, right?
Yeah.
So I wondered, can we find such path in a polynomial time always?
I see. So the difficulty is to find the vertex cover?
Yeah. So
Yeah.
we cannot find the minimum vertex cover in a polynomial thing.
Yeah.
So the proof looks like it does
Yeah,
not work.
yeah,
in
yeah,
the
that's crucial. So we didn't think about this before. I'm not seeing a resolution for that. I'm wondering about that. That's it, not a proof. If you will do some steps kind of random, so you have like a semi-random algorithm. If like in practice it would be solve it in polynomial time. Since our conjecture says that n plus tau is sufficient, so if you just want to prove that n plus 2 times tau is an upper bound, maybe you can do some recolorings at random, so that somewhat like you are far away from the worst cases, and then solve it efficiently, but not sure.
Yeah, thank you.
Okay. Well,
Okay, so are there examples of graphs that are not, it's kind of an opposite question of what we thought of, but I'm curious if you know if anyone's worked on it. Are there examples of graphs that are not GL of some other graph for any choice of another graph and L?
Wait, you want to know if every graph can be
Yeah.
found as a
Yeah.
configuration graph? Mind to-
Or I guess a broader question is, do you know if anyone's ever thought about this before?
Well, I know that people have thought a lot about reconfiguration.
Yeah.
So like Torsten Mütze has a recent survey on reconfiguration, which is not just about recoloring reconfiguration. And like he had like more than 60 open questions in
Okay.
that one. So people have thought a lot about reconfiguration. I didn't check all the stuff
I
they
see.
did.
Yeah.
So I have narrowed my space to investigate these type of problems. But my intuition is somewhat that not every graph can be
Yeah.
obtained, but I don't have like
Yeah.
an immediate argument for that.
That's comforting because I don't either. So now I feel better. I was scared I was asking a really stupid
Yeah,
question.
since, one thing I observed is, for example, if you have like the C6,
Mhm.
you consider all three colorings of this. So C3 of C6 is so C6 itself is like a regular graph,
Mhm.
but C3 of C6 is not a regular graph. So since like one of the intuitions one could have is, yeah, like for example, if you had like the K2, C3 of K2 is just a C6, like recoloring is as easy from every vertex. You can do equally many recolorings in every step. Like that's the intuition that
Yeah.
if you have a vertex transitive graph or like a graph for which the radius equals the diameter, that's not the case necessarily for reconfiguration graphs. So in some sense, some reconfiguration graphs are more complex than the initial. Well, they are at least larger in many cases. But they can be even like less regular than the initial one.
See.
Doctor, you also have a question?
So, is the course of this kind of reconfiguration graph is bounded or can be arbitrarily large?
Wait, did I?
Course of the minimum length
Cycle
of the
length.
cycle. Is it bounded or can be arbitrarily large? Maybe related with the data source.
Right. Yeah, it might be a 3, in which case it's different from that.
Unless tree course is bounded by 2 times diameter plus 1, isn't it?
I mean,
Isn't there a conjecture that it should be two connected if it's connected? Is that
Yeah.
is there any absolute?
Yeah,
Of course.
it's like about a uniform bound, like
Because it's
Well,
short.
exactly 3 colors.
that was the right.
yeah, also.
Yeah, right.
Otherwise, it's
Yeah. But like that other one is also like the counter examples do have just some leaves or degree 1 vertices. So in which case it's not too connected.
Oh, if even if there's counter examples.
Yeah, the counter examples for which are known for k at least 4
Right.
do have
I see.
leaves. So, but I think in this case it's about. So you want to have a reconfiguration graph which contains some cycles,
Yeah.
since trees are have somewhat like infinite girth, like because you can speak about a minimum cycle, and then if you have like a uniform bound, like mine. I think in many cases you will find a C4, since if you have like a very big graph, and assume there are some available colors here and here. So you want to color, for example, 1, 2, 2, 3, 4, and no neighbors do contain 1, 2, 3, 4, and you want to do the same here. You want to change 1, 2 to 3, 4. You could recolor first 1 to 3 and then 2 to 4, or you could do the reverse. Oh yeah, I even don't need a second edge. So basically then you recolor 1, or you recolor 2, you recolor 2, you recolor 1. You will end up in the same color. So in this case you have a C4.
So this means that the number of colors are maybe a bit larger than the chromatic number?
Yeah, indeed. So indeed, like this is a case which can occur if you have like big lists, for example, in the it's somewhat like, okay, we have some freedom to recolor efficiently, then you will have cycles, but in general it might be different. So I won't bet at this point, since there are weird things happening, since like with this 4x conjecture for k equals 3, they have like a precise characterization of the graphs you have to investigate. And so in that it's like, in that sense, they know all graphs you have to study. But on the other hand, knowing if such a graph, like if a graph satisfies that characterization, is again an NP hard or NP complete problem. So even while they know the precise characterization, since verifying that characterization can be done efficiently, you also, it's much harder to give an efficient proof. But which is a weird thing.
I have some nice question. So, I mean, in your abstract you mentioned about Rubik's Cube, but if I think about Rubik's Cube, the move will change not a single color, but
Yeah,
multiple
there are
colors
like
together. So that's
something like 21 which rotate, or 20 which might differ.
right.
Yeah.
But then does that, if you formalize such a situation in your context, is it going to change quite a bit, or it's the same?
Yeah, it's a pretty different problem. So in part 1 I was speaking about reconfiguration. So there are really many questions about reconfiguration. So like you might just change the graph by removing one edge or adding a new edge, and or you can play with dominating sets, with independent sets. So there are many ways for reconfiguration. So for example, as I mentioned, there is this really long, pretty long survey of Thorsten Mütze, where he considers many different directions of reconfiguration, somewhat, and quite a lot of these different sub-areas or different sub-problems on reconfiguration. Every time there are a few very interesting questions. So some people wonder about Hamiltonicity of a reconfiguration graph, which is very different with determining the diameter. But it's related a bit to connectedness again. So, maybe there are people who investigate like other problems about. So basically, also like the diameter of some other reconfiguration graphs, about games where you have some allowed change, and they really want to know about the diameter. So that's like the hardest puzzle, which is small. So it's like, oh yeah, you only have like 8 blocks, and to reconfigure this into this, you need to have like 2 to the 8 steps or something like this, which makes it interesting for people who are playing with this different types. So I didn't work on the Rubik cubes itself, but it was mainly about the thing about you have like one move, as was the case with the 15th puzzle, which is maybe like an easier case, but those are very different instances than the list.
So I mentioned about this Rubik's cube. I mean, one reason is it looks like it's changing the color of not a single vertex, but several vertices in one go.
Yeah, it depends how you are considering your vertices, since I'm thinking like the Rubik cubes has quite some group theory behind. So then instead of just having the 54 faces with a color, you maybe might look to the group theory and count like the number of generators in the group, and notice like, okay, we apply one additional group element, and then you are like considering the reconfiguration problem in a completely different way, and you have a different setting. Since that's the thing about colors. It's not because both objects contain colors that it's the same problem. I hope this is not too disappointing to you.
Well, it's okay.
Okay. Okay.
Right. I have one quick question. So,
Okay.
if graph is bipartite, then u is equal to tau. So,
Yeah, indeed.
I wonder whether one could conjecture that the diameter for DP coloring, the worst case appears when this is from list coloring, or?
No, that's not necessarily the case.
Oh, is it?
No, so for example, these swaps with the 1s and the 2s are like different in the DPs, like are examples in a DP setting which cannot occur in list colorings. But so there are bad cases in both cases, but obviously one interesting case to solve these conjectures are bipartite graphs, since especially like solving it in the DP setting also solves it.
Right, yeah.
And depending which strategy, sometimes it's easier to work with the matching number, sometimes it's easier to work with the vertex covering number. So, and like bipartite graphs seem to be an important case to handle first. But regarding sharpness, it's not completely true.
All right. Any other questions? Then if not, let's thank the speaker again.